Hi folks, welcome to another lesson in BCIT, Technology Teacher Education, TTED4010. This is our Arduino programming course for technology education teachers at the British Columbia Institute of Technology. And today we are going to take a look at blinkier and blingier things, in particular the Neopixel WS2812B strips. And you can see on my board right here, I've got one of those strips with the LEDs bouncing up and down on it. And we're going to talk about some of the reasons why NeoPixels, to use the Adafruit term, are so popular, so powerful, and so much fun to play with. Now, one thing you'll notice is that when I'm working with these, I do tend to put a piece of masking tape over top of them because they are bright. And more than once, I found myself looking over the top into there and really wishing I hadn't, as it takes a while for the blur to fade from my eyes. So let me just pull that off and show you a little bit about what you're going to need to follow along with what we're doing today. Okay, so what I have is I have an LED strip, and the LED strips come in all sorts of shapes and sizes and lengths. You can get them in a big roll, you can get them in rings, you can get them in arrays of 8 LEDs by 8 LEDs. And this particular one that I'm using with my class came from the website universalsolder.ca. And you can see on the back of it that we've soldered a little header strip on here at a 90-degree header strip on there with the long legs sticking out so that they can go down into the breadboard. And if you pay careful attention on here, you'll see that we have soldered to the, let me get the light right on there. There we go. We've soldered to the GND, the DI for digital in or data in, and the 4.7 volts. We haven't connected to this ground right here. We don't need that. Our information's coming in this way and our power is coming in this way. And if we had another strip, we could solder it on here and the data out would pass right through here and come along to our next LED strip. So you can get significantly long strips like this. And we're going to hook that into our board right here. I've got a whole bunch of other wires, but you can pretty much ignore almost all of it except for 3 of the wires that we're going to be using today. And what I've got in here is I have a power line at plus 5 volts coming right off here. I have a ground line, ground. I have a gray line, I'd say, got the GR in there. And on my board, that's coming over to A0. You could use any available pin on your board. It really doesn't matter. I tend to avoid using 0 and 1. Those are used for programming and serial communications. So I've hooked it up over here on A0, but if you had something free and, you know, on that side of your board, you could use that too. And then we've got a ground line right in here because, of course, on here, we've got a data in line. That my example, that's going to come from A0. And then we've got a ground and we've got a power. So just make sure that when you put it in the right way around. And there we go. And like I say, that can get pretty bright even through a camera. So a little piece of masking tape right over top of that can save you a little bit of agony on your eyeballs and still leave everything nice and visible to work with. Now, if you don't have this at home right now, you can play along for the home game a little bit because the Tinkercad Arduino Simulator also has NeoPixel or WS2812B strips available in here. And you can see here you've got one wire, 5 volts and ground. It hooks up the same way, and the data comes in here, and you can use lengthier strips. So all sorts of neat stuff going on. This is a range indicator. I've got a range finder on here, and as the range gets further away, the bar graph gets longer, and as the range comes in shorter, the bar graph gets shorter. The response time's not quite as quick because, of course, this is a simulated response. But if you want to experiment with WS2812B strips, go right ahead and work on here. They don't include the fast LED library that I'm going to be talking about today, but they do include the Adafruit Neopixel library. And if you go to Adafruit's website, you're going to find more than enough information to get that up and running. It is also a really powerful library, and I use both. Today I'm just happen to be talking about fast LED because I think in some ways it's just slightly better, but pretty minor. Anyway, so either one's going to work really well for you. If you're interested in seeing some of the things that I've done with WS2812B strips, here is what I call the Blinky Fish Head. If you Google Blinky Fish Head, you'll find a little instructional video that I put up online a while back for making lit animated bicycle helmets. And I go through all the different things you're going to need. And there is the LED strip right there. Um, and anyway, Blinky Fish Head if you're interested. Okay, now I've got lots of notes for you here today because I'm going to talk about not just the software that we use to get this running, but some of the hardware behind it. And so get your pens out and let's get ready to go. Okay, so the first thing I want to talk about is what do I mean when I say NeoPixel? Okay, now Adafruit, if you've been working with Arduinos for a little while, you're probably familiar with that name. Company founded by the internet famous, or the geek famous Lady Ada, and she founded a company that started making all sorts of really cool things so that people working in education with Arduinos and microcontrollers, or people doing DIY stuff at home, would have access to some really cool parts. And they've been very successful in helping promote the maker movement. So Adafruit, really good company, really engaged in making things in education, has some great tutorials on their website. And they came out and they put a brand name onto this chip right here. Now, the chip itself is called a WS2812B chip, and it's specifically designed for controlling LEDs. So I'll sometimes refer to these as WS2812B LEDs, but more correctly, it's the little chip on the LED, meaning that each LED is smart. Okay, now by smart, I mean that there's a standard RGB LED that you can get that's dumb. Okay, and all it is three LEDs packaged together into one casing. Okay, and you'll be able to recognize these because they have four legs coming off of them. One will be for power, and three will be, well, one for each color, and those will go back to your Arduino for control. Okay, so typically you'll have a red leg, a green leg, and a blue leg, and each leg will control one of the LEDs inside, and then you'll have power. Sometimes you'll have them most often be a common anode where plus 5 volts comes up in here and your Arduino syncs the power, but sometimes you'll have a common cathode where your Arduino sources the power and the LEDs are the other way around and power comes down that way. Doesn't really matter. It still takes 3 pins out of your Arduino, and it takes 3 of your analog right pins at that. So you really start to hamper what you can do as you start to add more and more of these. In fact, you can add maybe 2 to your Arduino, 3 or 4 if you really start to push things before things start to bog down quite a bit. And your Arduino spends all its time controlling those LEDs. With smart NeoPixel LEDs, your Arduino just sends a signal and the little chip on board the LEDs controls them. And that chip that does the control is the WS2812B. Okay, now just as with a standard RGB LED, we're going to mix the brightness to get the colors coming out of here. But instead, here's our, well, here's my sketch, and you can see right down beneath me there is a photograph that I dragged off the internet of a WS2812B LED. And if you look at it really carefully, make sure it's not on when it is, but if you look at it really carefully, you'll be able to see that there is a small chip on that LED, and that's the WS2812B chip, and it's built in there. And if you take your fingers and kind of go just like this, okay, and make a little pinhole like that, and look through it, okay. I know this looks great up here on the internet. make a tiny little pinhole and look through it at your super bright WS2812B LED, and you'll be able to see the individual LEDs on there. And it won't hurt your eyes, because if you make that pinhole small enough, not very much light will get through there. In fact, it'll work like a pinhole camera and help focus it. So if you've got bad close-up vision, you can maybe see it even closer. So on there are 3 LEDs, and I think I've kind of got the positions right on here. Doesn't really matter if I don't, but there's a red, a green, and a blue LED on there, and a chip controlling it. Now, those are all hooked up to 3 lines coming in, and we were talking about them when we were saying how we were going to hook this up. There's a plus 5 volt line, and Neopixel's WS2812B chips are really fussy about this being 5 volts. Don't try and run it at 6 volts. They don't like that. And the sad part is if you burn out one of these chips in a strip, then that can cascade down the line, or this can block whatever's going on, and you can't get your data through it. Because what happens is you've got one pin on your Arduino, and we're going to talk about how the Arduino sends data down this line, and it sends it 1 bit at a time right in here, and this chip takes off the first 3 bytes of the data, 1 byte for each of red, green, and blue, and sends the remaining data out this way onto the rest of the LEDs in the strip. Okay, and each pixel is going to suck off 3 bytes, because it needs 1 byte for controlling red. Okay, a number from 0 to 255 takes 8 bits to convey, or 1 byte. 1 byte for green, and 1 byte for blue. So if you've got 2 LEDs, you're going to need 6 bytes, etc., to control their brightness. But the cool thing is, because we're sending this data down one line, one Arduino pin, by sending 1 bit after the other, can control hundreds of LEDs. Okay, now a few things to keep in mind when you're hooking these up is that each LED at full brightness draws about 20 milliamps. That's pretty standard for an LED. Okay, somewhere in the 10 to 20 milliamps range is pretty standard for an LED. 20 milliamps is pretty bright, but these are, as we've seen, super bright LEDs. Okay, now normally that's not a big issue, but there's 3 LEDs in here. And on that little board that we were looking at, you've got 8 LEDs. So one bright white NeoPixel where all of these are turned on. So you've got red, green, and blue all mixed together, so it looks white. That's drawing 60 milliamps. And if you've got 8 of them all hooked up like you do on your strip, that's going to draw 480 milliamps. Now, what does that mean? Well, a standard computer USB port is guaranteed to give you 500 milliamps, so the strip that you've got probably won't blow a fuse or anything on your computer's USB port. But if you get up to strips of 20 or 30 LEDs and you happen to turn them all at the same time, that's going to be an issue. That Blinky Fish Head that you are looking at that has well over 100 bright white LEDs on it, I think I had 140 or 160, you'll notice that they never all went on at the same time. Because if they all went bright white at the same time, they would need 6 amps. Actually, on that one, I think it was going to need something like 9 amps, and I was just running it off of a little battery that could supply maybe 1 amp. So when you start to use big arrays of these LEDs, if you want to, you can make them really bright, but you need a really big power supply to do it. Okay, well, anyway, big power supply or not, these LEDs are really cool. How does this dark magic work? Oh, I already worked my pun into the notes. It was a good pun. I didn't want to forget it. How does this light magic work? Okay, now I'm going to dig in a little deeper than I sometimes go with this. So I'm going to be shoveling the Technobabble with a big snow shovel out here, okay? So here's some technological terms that I'm going to assume you already know, even if you really don't understand them. Now, if we go through all this and you're like, Jason, you went through them pretty quick, I don't really understand them, and this is the first time that you're seeing them, then that's okay. All right? It's probably the second, third, fourth time, yeah, but maybe you've never really dug into them. And it's like learning any kind of language. Being exposed to a term multiple times, all of a sudden you start to say, oh yeah, hexadecimal, I know what hexadecimal is. So if you're already familiar with hexadecimal, feel free to skip ahead in the video a little bit. And if not, let's just do a quick little look at this and remind ourselves what hexadecimal is, because I'm going to be talking about hex a little bit later on. Okay, now hexadecimal is a counting system used by computer scientists. Okay, we use it a lot. And it's really convenient for expressing binary numbers, which, as we know, is what computers are all based on. So in our standard decimal counting system, we come down here and we use 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then by the time we've gone 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we've ran out of fingers. So what we say is that we've got one group of 10 and 0 extras. Then we've got one group of 10 and one extra. We call that 11, 12, 13, 14, 15, 16, 17, etc. Okay, now that works out really great for humans because we've got 10 fingers and we work on a base 10 system. But computers work in binary, a base 2 system. So their memory locations are either on or off. It's like trying to count if you've just got one finger. Okay, you'd say 1. Okay, well, now I've got one set of one finger and no extra fingers. And then I'd have one set of one finger plus one extra finger. And now I've got one set of, anyway, it goes on like that, okay? And in decimal, we refer to this as the ones column, the twos column, the fours column, and the eights column, okay? So if I wanted to find the number 7, I've got a 1 in the 4 column, a 1 in the 2, and a 1 in the 1. So 4 plus 2 plus 1 gives me 7. Now, hexadecimal works exactly the same way, and it comes right along here until we get to the number 9. And once we get there, we're like, hey, we're having a good time in hexadecimal. We don't want to stop. In fact, we want to keep going with hexadecimal all the way up, A, B, C, D, E, F, until we get to the binary number 1111, which is 15. Okay, and you'll notice that this is a 4-bit binary number. Okay, so what's great in hexadecimal is that we can express a 4-bit binary number with one character. Now, why that matters is because 4-bit is 1/2 of a byte. And so we can express any byte value using 2 hexadecimal numbers. Okay, so anyway, we come up here, 1, 2, 3, 4, 5, F is the decimal equivalent of 15, the binary equivalent of 1, 1, 1, 1. 1 in the 8s, 1 in the 4s, 1 in the 2s, 1 in the 1s. Now, as we go one more past there, we do just like we do in the decimal system. We put a 1 into what we'd call the 16s column and a 0 into the 1s column. So we've got one group of binary numbers, or one group of hexadecimal numbers, I should say. We've got 116 and 0 extra. And you can see right here, now I've got a 1 in the 16s column and nothing in the other columns over here. And I start building up my second binary number. So if I come up to a decimal number like 32, which is 2 groups of 16, 32 in decimal is going to be 20 in hex. Okay, and if we keep coming down a little bit further, we'd get to a number like 196, which would be C4, okay? Because C is our decimal equivalent of 12, so that means I've got 12 in the 16s column, so 12 times 16 gives me 192, and a 4 in the ones column plus 4 gives me 196 right in there. Now, part of the reason we really like this, being computer scientists, because like most engineers, we're kind of lazy and we like to find easy ways to do things. And that means that if I need to figure out which bits are activated, because sometimes we'll use the bit pattern to turn individual pins on and off or individual flags or states on and off for marking things, we want to be able to quickly translate a number like C4 into a bit pattern. Well, I don't have to go back and do a whole bunch of math. I know that C is 1100, so I just put 1100, and 4 is 0100, and all of a sudden I can go from hexadecimal to binary and back again really, really quickly. Add that to the fact that my biggest hexadecimal number that I'm going to use regularly for 1 byte is just 2 characters. I hit FF when I'm at 1111, 1111. In decimal, that would be 255. So when I'm printing things out and trying to look a big long list of data, it's much easier to display it in hexadecimal because byte values can be expressed with 2 characters instead of sometimes 3, sometimes 2. Okay, and we can translate those patterns back and forth into bit patterns really, really easily. Okay, so you're going to see us make some reference to hexadecimal, and you'll also see us use in the Arduino language, we'll start numbers beginning with 0x. So if you see a number that looks something like 0x F3, okay, or F34A for a 2-byte number, okay. If you see something like that pop up and you see this 0x at the beginning, that means that the number is going to be in hex. And that's just a heads up to the compiler that it should interpret that as a hexadecimal number. Okay, 0x. That's not a very clear x. There we go. It doesn't say aux, that's actually a 0. Okay. Alrighty. Now, so hexadecimal is one of those terms I assume you know, and you'll see hexadecimal numbers pop up from time to time as we go through this little lesson. The second term that you've probably heard before, and I've mentioned it, is the compiler. Now, when you're running your Arduino IDE, so the IDE is your integrated development environment, you're actually writing your data into what we call an editor. And then when you press the upload button, you'll see a bunch of things happen, and you'll probably see the word compiling pop up at the bottom of the screen. Now, what's happening when you compile is that you're taking your source code and having it translated into machine code, which is known as a hex file because the data is all in binary, but it gets expressed in hexadecimal. Yeah, another bad pun. Another bad pun. Oof, what the heck is going on? So the machine code is in the instructions that the chip understands. Like the chip doesn't understand what digital write means. That's something that we've written for humans to understand, okay? That sort of makes sense in English. Probably doesn't make a lot of sense in Japanese, but you know, if we're working in English, digital write is a command that makes sense to you, okay? Well, it makes no sense to the commands on the chip. The Arduino and all microcontrollers and all CPUs speak very simple languages. And let me just flip over to the Arduino's data sheet, and I'll show you a little bit about what those commands look like. Okay, so here we are, and I've gone and Googled Atmega 328 instruction set summary. And right here, we've got a list of all of the commands that that little chip on your Arduino actually understands in its own language. And these it understands because they're baked into its silicon. Okay, when they designed this chip, this is how it's designed. Now, it doesn't actually understand the words right here. Like this says add, it's an arithmetic and logic instruction. There will be a numeric code for add. We just call it add because, again, we're humans and we understand that better than trying to remember the code number F3. Remember, F3 is a number in hexadecimal. That code F3 or whatever it's going to be is an add instruction. And we've got 2 types of add. You can add with or without a carry, and one's going to execute a little bit faster than the other. And so if we scroll down this list, now this is just the summary of instructions right through here. And this is actually a fairly extensive set of instructions. Before I started using Arduinos, I used something called the PIC microcontroller, and it used what's called RISC, R-I-S-C, reduced instruction set computing, and so that they could build a simpler chip with fewer instructions, and could do each instruction a little bit faster. The Arduino has more instructions, but it might take a little bit more overhead on the processor in order to run them all. So this is a rather extensive list of instructions coming along here. And then when you get past the big long list of instructions, okay, you get in here and it's got an explanation of what each instruction does. And I'm not going to hang out too much time there because, well, assembly language is really cool, but it's beyond the scope of this course. I know you're disappointed to hear that. Now, the reason I mention this is because in order to get the WS2812B strips working, we're actually going to have to use a bit of assembly language or machine language code, although you don't have to write it. You don't actually even know that you're using it, but it's good to know that it's there and that it's running in the background because we're going to do things that you couldn't possibly do directly from the Arduino IDE. I mean, we're going to do them from the Arduino IDE because that's how you know how to do them, but we're using somebody else's assembly language instructions because writing in this assembly language is much more basic than C, allows you to have much more precise control for programmers who use it directly. In fact, just before I go on, I'm going to show you a program that you're really familiar with, the Arduino's Blink program, and I'm going to show you what it looks like in machine language when it gets loaded onto your chip, and then give you an idea of what it looks like in assembly language. And no, you don't have to know how to do this, but it's good to know that you've got this fancy thing called a compiler, which is a piece of software going through and taking your source code and turning it into compiled code to put on the chip. It's also the answer to the question of, well, I didn't save my source code, Jason. Can I pull my code back off of the Arduino? The answer is yes, but it probably won't help you. All right, let me show you what that looks like. Okay, so here I've compiled a program that you're really familiar with. Blink, okay? Turns an LED on, turns an LED off. Really, really simple code. In fact, let's see right on here, Blink. Here's the Arduino Blink code, right? Digital write, A0 high, digital write, A0 low. Not a heck of a lot to it when we put it in human language, okay, in the source code, because each of these commands is doing a lot of things for us. Now, what happens when that gets compiled is that you end up with code coming out, something called a hex file. This is what's going to go onto your Arduino, okay? And you can actually, let me just clear the parts where I was searching there. I'll show you what I was searching for in just a minute. But this is what's going to end up going on your Arduino. In fact, this first little bit of the line right here and the last little bit of the line doesn't get stored on the Arduino. They're just there to make sure that the key bits right in the middle do go on your Arduino and that your Arduino gets them correct, okay? So here we go. You can see a whole bunch of numbers in hexadecimal format, and the entire Blink code is not all that long, okay? But it sure looks different in machine code. Now, this code right up here is all in numeric or hexadecimal code. It's actually going to be transferred into storage on the computer in binary, of course, because it's all ones and zeros. But we can sort of pluck apart and take a look at some of the instructions on here because we have something called a decompiler. Now, this will never get it all the way back to your source code, but if somebody knew how to read assembly code, they could go in and they could start figuring out what this code was doing by going through it step by step. So you could pull the code off the computer, but unless you know how to read assembly code, you're not going to be able to do much with it. And really, you're going to have a hard time getting it back to source code. But anyway, here we go. So here's the first command that comes up right in here. And you'll see that it has an opcode of 940C. Okay. And then it's got a modifier down here of 005C. And what that's telling it is to do a jump in the program memory to hex location 5C. So if I'm looking for this bit right here, 940C, there's a 94 in this first line of the code right here, okay? And there's a 0C right before it. In fact, they're written in reverse format. Yeah, just to make it easier, right? And for our 5C, okay, here's that 5C, and then 0, 0 right there. So that sequence right there, okay, that I've highlighted in blue, C945, C 0, 0. Oh, sorry, missed 1 0 on there. That sequence right in there tells your microcontroller to jump ahead in program memory to location hex 5C. So if I come down right in here, okay, you can see the addresses are all in here. Each is in a memory. So that program, the very first thing that it would do would come down here and jump forward to memory location 5C, where it would find the opcode 2411. Okay, and if I search, remember it's backwards, for 1124 in here, this pops up right in here. Okay, and where was I? 5C right in here. 1, 2, 3, 4. And that's going to execute the EOR command. And I looked that up earlier, and it's an exclusive OR between register 1 and, in this case, register 1, and it puts it back into register 1. I'm not 100% sure what that one's doing in there for us. Like I say, I'm more of a PIC microcontroller assembly guy rather than, and even that was a long time ago. And then your next command down here would be BE1F, and you can see there's the BE right in here. Oh, I didn't want the whole line to light up. There's BE right there. There's the 1F. And anyway, it goes on from there. So that's what your compiler is doing for you. And when it comes time for us to get really precise and we need really, really careful control of timing, or we need really, really fast responses, we need to break away from the Arduino language, and we need to let somebody actually get in here and write some assembly language or machine language so that we can directly control what's going on the board. So it's a neat thing that's happening for you automatically when you run that compiler, and it's nice to appreciate the people that wrote that code that can take your human language program. I know it doesn't seem too human sometimes, but it's sure a lot more human than this. All right, and turn it into something that the chip can use. And the cool thing is that there's compilers for all sorts of different microcontrollers. So the code that you write for your Arduino Uno that runs and is compiled for an Atmega 328 microcontroller, if you use a different compiler or a compiler with different settings, you can actually compile that and run it on a whole range of different microcontrollers just by compiling it with a different compiler. And the same thing goes for computer software too. Depending on how high level the language you write it in is, and a high level language refers to one that's far away on the English scale from the and from the human comprehension scale from the machine language scale. The lower level languages, we're using something kind of in the middle with our version of C, get a little further, a little closer to what we're doing down here. Anyway, compiler, machine language, assembly language, important terms to be able to understand when you're working with microcontrollers and computers. Now, as we go along, you're also going to hear me talk about clock speed. And in fact, you've probably heard people talk about clock speed on their computers quite a bit. I overclocked my computer. I'm running at 3 gigahertz or 4 gigahertz or whatever. Well, on your Arduino, the clock speed is controlled by a little crystal, and it's probably in a shiny little metal container like this one right here. This is anyway, one place where you can have it. And if you look really carefully at it, somewhere on there, it probably says something like 16 megahertz, because your Arduino's heartbeat, which comes from its clock speed, okay, it's the rhythm that knocks everything out, is a 16 megahertz chip, or 16 megahertz crystal, and that's creating a signal that runs 16 million times per second. And that is like the drum beat running all of the commands. Everything on your chip is synchronized to happen 16 million times per second. 16 million times per second sounds kind of fast, but keep in mind we were talking about your CPU on the computer being like 4 gigahertz. That's 4,000 megahertz, okay? So your Arduino's at 16 and your computer's running at 4,000. So part of the reason why your computer can process things faster and also why it generates more heat and needs more power. It's got like the hummingbird heartbeat going on in there. Okay, now one of the downsides to having the slower clock speed or the slower heartbeat is that although it's going beat, beat, beat 16 million times per second, that means that we get one beat every 62.5 nanoseconds or billionths of a second. Okay, so the absolute fastest thing an Arduino can do is still going to take 62.5 nanoseconds. Now, this is in reference to the Arduino Uno. There's newer, faster Arduinos on the market, but our good old classic Arduino Uno is thankfully fast enough for just about everything we need to do. Okay, now the other thing is that many instructions require more than one heartbeat to execute. So if you're adding a simple number, that's going to take 3 or 4 clock cycles, maybe more, to happen because you've got to go get a number out of memory. You've got to do the adding operation, then you've got to put the number back into memory. And if you're dealing with a 2-byte number or a floating point number, even worse, okay, then you've got to do a whole bunch of numbers to say, oh, was something carried from the first operation? I better store that over here and use it to the next operation. So a lot of these commands that we're running are going to take more than 62.5 nanoseconds. Now, if you're programming in machine language, you can control the specific commands that are being used. But if you're writing in the Arduino IDE, you can't really. Okay, so we've got a couple of things that we need to keep in mind, and I want you to keep in mind that 62.5 nanoseconds for the fastest thing that we can do. It sounds really fast to do something in 62 billionths of a second. Yeah, well, it's going to be tight when we come time to talking to our NeoPixels. All right, now part of the reason that clock speed matters is because to get our data from the Arduino onto the NeoPixel, we're going to use serial data. And we're going to transmit one bit of data right after the other. Now, we've talked about serial data before. It's used by USB. So your universal serial bus that you plug into your computer, the way you get data from your flash drive into the computer or from your computer to just about every peripheral that it uses right now, it's running over the universal serial bus. And it's running a lot faster, 10 to 100 times faster than we're going to be running our NeoPixels. Okay, your Arduino's UART. Okay, that's the fancy word for that serial port that we use all the time. Okay, when you go into Device Manager and look for the COM port that you're on, that is talking about your serial port. When you say serial print, you're actually using a universal asynchronous receiver and transmitter. But because it sends the data one bit after the other down one wire, okay, we call it a serial port. And it's got a receiver and transmitter on here. So we've got one line being used for transmitting, okay, so it's going that way, and we've got one line being used for receiving, it's coming that way. So there's 2 wires on there, but they're each only transmitting in one direction, okay. Other famous serial protocols include Morse code. And of course, what we're going to do today, the NeoPixels. Okay, this serial data is different from the parallel data that we use for your LCD screen. Okay, you'll recall when we were wiring up your LCD screen that we had to run a whole bunch of different wires in here and that they're still hogging a whole bunch of ports on our Arduino. Okay, that's one of the downsides of parallel data is it uses up a whole bunch of your microcontroller pins and it requires a whole bunch of different wires. But the other glitch that comes into play with parallel data is that in order to transmit a lot of data quickly, you need to be able to send it and have it all received at the same time. What's really cool, I mean, so parallel data was really common in older computers because we couldn't get our clock speeds high enough to send data super fast down the serial lines. But as we got our clock speed faster and faster and faster, we could send the data faster and faster down the lines. And all of a sudden, what we were discovering was that because this wire is a little bit longer than this wire, that this data was getting there first, and this data was receiving its bit before that data that pin was. And now all of a sudden we had to wait for all the data to get there. So even though they could make the data transmit faster, they couldn't get it down a parallel line fast enough. So at some point, about 10 to 20, I guess 10 to 20 years ago kind of covers it, there was a big shift in communication protocols from parallel and using multiple pins to serial and just using a single pin, because now there's only one wire, so the bits will get there when they get there. Still creates an interesting problem, and if you ever read about the computers that they use for doing the stock markets, they actually make sure that different trading houses have similar length fiber optic cables, to the point where they'll take big coils of fiber optic cable and leave it sitting in the basement of the central exchange house, just so that with all the fancy computer trading algorithms that are out there right now, when the trading companies send their data in and get their data out, everybody's got fair access to the central computers. Yeah, interesting stuff going on when we start looking at serial data. Okay, I'm almost through the Technobabble section here. The other thing that we're going to do is we're going to use an oscilloscope today to take a look at the electric signals that we have running through our Arduino. And let's see, I'm going to show you the oscilloscope that I have sitting here on my desk, and then we'll talk a little bit about what it does a little later on. At some point, while hauling the camera around on my desk to show you this view, I whacked the mute button and lost all the audio. So I'm editing this back in right now. And that's the scope. The thing in my hand right there is the DP scope that we'll build in our next electronics course. So, yay. Audio works now, thanks to editing. Okay, now that we know what a NeoPixel signal might, well, now that we know what an oscilloscope is, let's take a look at what a NeoPixel signal might look at or look like, so that we can view that signal on the oscilloscope and see what's going on when we execute all our fancy NeoPixel commands. Now, it takes 24 bits of information to turn a NeoPixel on. Okay, 8 of those bits are for the green byte, 8 for the red byte, and 8 for the blue byte. So we'd have bit numbers 0 through 7. So for instance, a string of data like this, 001, 0000, if we were sending that down the line, would tell us that our green would be set to 16, because our 0 bit, that's our 1, 2, 4, 8, and there's our 16 bit is turned on. So our green would be set to 16, which would be dim. Okay, and keep in mind that this is going to be like a pulse width modulated thing, so it will be off most of the time, on a little bit of the time, and it'll blink so fast that it just ends up looking dim to us. Our blue, if we send 11111111, or we could also refer to that as hexadecimal F. F, okay, that would be 255 or full. And if we sent 0000 all the way down to our red, that would mean that the red LED would be off. Okay, so for each LED in the system, each pixel, you're going to see 24 bits of data streaming down the line. And when you see a 1, well, that's part of the data. And when you see a 0, that's part of the data too. Okay, now each of the 3 pixels, therefore, takes 3 bytes, 24 bits of information. then passes on the rest. So if we've got multiple pixels, our Arduino will sit here and say I've got a 4-pixel strip. It will send 12 bytes down here. And this pixel will grab the first 3 bytes that come in and say, right, that one's for me. And then it will pass the remaining 9 bytes on to the next NeoPixel. Okay, and it'll see the first 3 bytes that come in and say, great, those are for me. And it'll pass 6 bytes along to the next one, which will, as you can guess by now, take 3 bytes and say, those are for me. And then it will take the last 3 bytes and pass it along to this LED. And this LED will have nothing left to pass on to anybody else if we've set it up properly. If we've got the number of LEDs wrong, this LED might still be sending data down the line and there might be nobody there to listen to it. So it's okay if you tell it that you've got 20 LEDs and you've really only got 4, you're just going to have one lonely NeoPixel at the end of the line. Little WS2812B chip being very sad that it's nobody to pass that data on to. Right. So what does this data look like? Well, a 0-bit is a short high pulse. So if you see a pulse go high for 400 nanoseconds and then low for 850 nanoseconds, okay, so blip blip like that, then you're sending a 0. And a 1 will go high in the exact opposite pattern. So it goes high for 800 nanoseconds and low for 450 nanoseconds. Now, you have to get the timing on this pretty precise. You are allowed a tolerance of plus or minus 150 nanoseconds. But if you're not within that timing spec, then your WS2812B chip isn't going to understand what you're saying. Okay, it's not even going to try. It gives you a fairly wide range of values in here, like 400 plus or minus 150. I wish some of my math questions came in like that. Oh yeah, you're good if you're within 30%. But really, it does require very precise timing because you might recall that we said the quickest thing that an Arduino can possibly do, an Arduino Uno running at 16 megahertz, the quickest thing it can do, machine language or compiler, anything like that, it can only be accurate to 62.5 nanoseconds. So really 62.5 doesn't divide nicely into 400. So thank goodness they give us a bit of tolerance in here. Okay, so we can see 0 bits with being on for a short period of time, 1 bit on for twice as long. Okay, now the combined time between these two. Oh, I should mention, if you see a low pulse, so if it just goes low like this and stays low for a long time, like 50,000 nanoseconds, which sounds a lot when we say it in nanoseconds, but that's like 50 microseconds, which is less than a delay of 1. It's a fraction of a millisecond in there. Okay, 50,000 nanoseconds. So if it stays low, that indicates the end of the data. So these chips can all go through and they can reset and they can say, right, now I'm going to grab the next 3 bytes that come through. I'm going to grab the next 3 bytes that come through and all over again because they need to know when they can start grabbing data again. And that signal is when it goes low for a little while. So we've got 3 things that we need to do to send data. Go high and then low to indicate a 0. Go high for twice as long and then low for half as long to indicate a 1. And then we've got to go low at the very end of the data to indicate that we're at the very end of everything. So 1 bit of information takes 800 plus 450 nanoseconds, either the 400 first and the 800 later, or the 800 first and the 450 later, but it takes 1250 nanoseconds to send 1 bit of information. Now, each NeoPixel is going to require 24 bits of information, okay, because it's 3 bytes. So 24 times 1250 gives us 30,000 nanoseconds, which again sounds like a lot, but that's 30 microseconds, 30 millionths of a second when we're talking in here. Nanoseconds are really, really tiny, billionths of a second, okay? And then over here, we've got, if you wanted to control 100 pixels, well, that would take 300 bytes. So you'd have 100 pixels times your 30 microseconds. okay, would give you 3,000 microseconds, and that data would flow down the line in 3 milliseconds, because 3,000 microseconds is the same as 3 milliseconds. Um, but anyway, that's about the same time as it takes to do a delay 3 statement on your Arduino. And normally we do things like delay 10, delay 100, delay 50. So it's super fast, really. And it's still considered a relatively slow serial communication protocol. Now, the problem we run into is that when we go to send data down the line, okay, digital write takes 3.5 microseconds to execute. That's 3,500 nanoseconds. So even if we wanted to try writing the code ourselves in the Arduino IDE, we couldn't even come close to doing it with digital write. I'm going to show you what digital write looks like on the oscilloscope. Okay, so here we've got the code that's running. I'm running the blink routine, but I got rid of the delays. You can see right down here, I've commented the delays right out of there. So all this is doing is it's digital write high on A0, digital write low on A0. It's doing it as fast as it can. There's nothing else in here from our Arduino code. And this is the signal I'm getting on my oscilloscope. Okay, now a few things about your oscilloscope and what we're looking at right on here is basically we're looking at graph paper. Okay, we've got voltage coming up and down. So voltage is vertical right in here. And you can see right here that this one marks where the axis for channel 1 is. I've got 2 channels that I can use on this scope. The ones that you have in the lab have up to 4 channels, which is a bit of overkill for the stuff we do, but it's nice to have anyway. So we're looking at one channel right here, and this is 0 line. So where I see this 1, that is the 0 volt line for channel 1 that we're looking at. So when I'm right in here, I'm at 0 volts or I'm at low. Now, you can see right down here that it says 2.00 volts. That's 2 volts per division. So that means that each of these divisions right in here, this is 2 volts. This is another 2 volts. So I've got 2 volts, 4 volts, 6 volts right up here. And I'm running at just a hair over 5 volts, which, you know, nice power coming off my USB port right here to drive this thing. Comes along right here, and then it goes low. And so when I do my digital write low, it immediately plops off the edge right there. It stays low until it sees digital write A0 comma high, and it jumps up right there, stays high, and then it sees digital write low again. Now, the voltage tells me my vertical axis. My horizontal axis is this number right in here. And this is telling me that I've got 1 microsecond per division. Okay, so in other words, coming across this way, if I count this as my 0 axis, then I've got 1 microsecond, 2 microseconds, 3 microseconds, about 3.4 microseconds for the commands to execute to go from high to low using digital write. In other words, doesn't matter how fast you write your Arduino code, you're going to be turning those LEDs or turning the pins on and off at only 143 kilohertz or 143,000 cycles per second, which is about 1/8 of the speed that we need to actually send data down the line. This is just nowhere near fast enough. So we're going to have to find a faster way to get data out our data line and to the NeoPixels. Okay, so what are we going to do? Well, one thing that we could try doing is something called direct port manipulation. And I'm not going to get into that right now. I know it sounds like something your chiropractor is going to try with you someday, but direct port manipulation is a way of skipping past that very slow and pokey digital write command. So if you're interested, give it a Google, Arduino direct port manipulation. You can do it from in the IDE, but even then, and believe me, I tried. I wanted to make this happen using without going into the library. You're not going to get fast enough to turn your NeoPixels on and off. So we need to find somebody who's done some work in assembly language for us, a bit of machine code programming going on right here. And several libraries provide this service for us. Now, earlier I was using Tinkercad and I mentioned Adafruit's NeoPixel library. Works great, no complaints. I've used it many times. I like it. And if you're using the Tinkercad simulator, it's the only one that you've got available. I slightly prefer the FastLED library. Okay, it's a little, I guess in some ways it's a little geekier. It's got some fancy math built into it, and it really does run fast, like they say. It's about as easy to use as any of them. There's a few things that you need to do, and you need to get your head wrapped around the aspect that you're building up an array of data, and then you're cramming it all down the line all at once, okay? So we're going to use FastLED. We're going to install the FastLED library into our Arduino IDE, and then we're going to take a look at the example called Blink, and we're going to make an LED blink using the FastLED library. Okay, and then we're going to take a look at how we can make it show the colors that we want and how we can end up animating that. Okay, so just like any of the libraries in here, to get a library into your Arduino, you need to come into your tools and come into Manage Libraries. And this has been a nice improvement that they've made in the last 5 or so years to the Arduino. You used to have to go out and manually bring the libraries in and install them in the right folders. Now, pretty much all of the registered libraries that are good for Arduino are out here. And when you open up your library manager, you can just type in FastLED. And it will go out and it will search for all of the libraries that have FastLED in the name. And you can see that some are designed for the NeoPixel matrix grids. Some are designed for other things. They're optimized for various things. We're looking for the one that just says FastLED version 316, or maybe there's a newer version out there now by Daniel Garcia, okay? And when you've got that, mine just says update, yours should say install because I've already got it installed on my system. If you wanted to compare it to the Adafruit NeoPixel, okay, you can just type in Adafruit. Well, actually, if you type in Adafruit, you're going to get a whole bunch of things. Type in Adafruit NeoPixel. And the one that you want is not the DMA NeoPixel library, not the NeoMatrix. You want the Adafruit NeoPixel library. It also works great. Today we're going to be talking about FastLED, but feel free to play around with these other libraries. A lot of people have spent a lot of time working on them to try and make them usable for you. Okay, now if you've got the FastLED library installed, you'll know it all worked well because when you open up your examples, somewhere down here, as you can see, I got a lot of libraries and a lot of examples in here, but somewhere on your system, probably closer to the top than this, you're going to find FastLED. And usually, when you're doing a lot of computer languages, there'll be something called Hello World, which will be your first program that shows off how something works at its simplest level. But a lot of the stuff on microcontrollers, it's all about blinking an LED. So let's take a look at Blink. And here is the Blink file. Oh, wrong Blink. I've already got it open, so I don't need to save those changes. We had that window open. All right, here is the FastLED Blink file. Actually, I'm going to close that so that I can show you the changes we have to make to Blink to get it working on our system. File, examples, FastLED, Blink. Okay, sorry, a little bit confusing on there. We've got this. I was playing with it earlier. I'd made some changes, and I don't want to forget to tell you about any of the changes that we need to make. All right, so anytime that we're using one of these NeoPixel libraries, because our strips can be really long, up to hundreds of LEDs, So what we want to do is we want to define the number of LEDs that we're working with. So whether you're using Neopixel library or the FastLED library, you're going to see something in here at the beginning that says how many LEDs you're talking about. And for Blink, one. We're just doing one to start with. Pardon me. And then you're going to need to tell it what data pin you're using. Now on my board, I've used A0 because that was convenient for me. You don't have to use A0. You can use whatever pin you've plugged that data in pin onto on your Arduino. Okay, we don't need to worry about the clock pin. We're doing an asynchronous serial, meaning that we don't have a clock going and beating out a time. That would be a synchronous serial signal if there was a clock pin going along like that. There are some serial protocols that are synchronous. We're using one that's asynchronous. So we don't have to worry about a clock pin. Okay, there's different types of Neopixel's not the brand name. There's different types of displays that do use clock pins. Okay. Now in here, this command is important, but you can see it already draws on something that we've changed in control. So it's created an array. You'll recall in our previous videos, we've talked about arrays. They've got these square brackets around them, and it allows us to store multiple copies of one type of variable. And this is going to store a type of variable that our library has defined for us called the CRGB. And we're going to name that array LEDs. You could name it something else, but just keep in mind that anywhere where you see LEDs show up in here as a word on its own, you'd have to change that as well. Okay, now in the setup right here, it gets a little confusing because of all the comments in here. Now the comments are all for using this with different types of chips. We're talking about the WS2812B chips because they're super common, and you know, if you go online, they're probably the ones that you're going to find. But there are other chips out there that do something similar to this. So this FastLED library has been designed to work with all of them, but you can see the line that it's got chosen for us right here is FastLED, add LEDs, Neopixel data pin. We have already said what the data pin is, and we've linking it together with the LEDs and the number of LEDs. So this command's a little bit obscure, but all you need to do is copy it into your code if you're writing new code, okay? It's a critical command. In fact, it's probably the exact same as the command right above it, but never mind. This line is going to work for the LEDs that we've got. All the rest of the comments, you can delete them if you want. They're not important to us. Okay, now down here in our loop, this is where we're going to turn the LED on and off. Now, right here, you'll recall that we set up an array called LEDs. And because there's only one LED in there, there's only one element in that array, and that's element 0. If we had told it that there was more LEDs, we'd have LEDs square bracket 1, LEDs square bracket 2, LEDs square bracket 3, etc., all the way along. And what we could do is we could put a color value into each of them. In here, it's going to use the format of using its CRGB math, and it's going to look up a table, and it's going to say, well, I want the color red. And this is designed so that you can just type a name in and people can understand it. I'm going to show you a couple other ways where you can do this numerically as well. And then it executes the FastLED.show routine. Now the show routine really matters because what it does is it takes this array of data that is sitting in the Arduino's memory, and this is where it crams it all out, the pin. And that's where it makes the pin go pulse, 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 pulse to send those 24 bits per LED down the data line so that we can set the colors. Your LEDs will not change color until you say FastLED.show. Then it does a little delay in here just because that's what Blink does. If you don't leave it on for a bit, humans can't see it. And then it says LEDs.0 equals CRGB black. in other words, off. Okay, and then it does that FastLED.show again and sends the data down the line. Let's take a look at what we see on the oscilloscope when this data is coming through. Okay, I uploaded the code onto my Arduino, and you can see right down here, I've got a blinking LED. It's turning the red on and off, and I've captured a little segment on the oscilloscope right here. Now, in order to get the entire thing onto the screen, I had to go to a 5 microsecond delay. So my bits are coming in really, really tiny. We can zoom in on them in just a moment and see a little bit more detail of what's going on. But let's just take a quick count and see our data coming in right here. So I'm looking at the pin that's carrying the data. And right in here, you can see 1, 2, 3, 4, 5, 6, 7, 8 short pulses. Okay, coming in right there. Well, those 8 short pulses are 8 zeros, and that represents the zeros going to the green data, going to the green memory location. So that's why I don't have any green showing up in there. Actually, I'm just looking at the screen. It kind of looks green because I got the tape on there, but it's definitely showing up red to my eyeballs. There you go. I think you can see that a little bit better. Now, the next 8 bits are for red, and here you can see that we've got longer pulses and shorter off times, which indicate our 1 bits. So here's 1, 2, 3, 4, 5, 6, 7, 8 1 bits coming through there, indicating that the red is set to 255. And now we've got 8 0 bits, these short little pulses, 1, 2, 3, 4, 5, 6, 7, 8 coming in there, indicating that our blue should be all turned off. Okay, so that signal right there should be turning on my red. Now, let's see if I can capture a signal for black. And I'm just uploading that from the scope right now. And here's a signal for black, and you can see again, I've got 24 pulses coming in here, but this time they're all short pulses. So zeros all the way along. So when I send the black data down there, it's just 0 in each byte. Okay, let's try changing the color and see what we get coming out of there. To change the color from red to green, I'm just going to come over here to my Arduino IDE, and I'm just going to type in green. And I'm going to upload that to the Arduino and bring my display back up here and see if I can capture a green bit. Definitely seems to be pulsing green. Just pushing buttons here, trying to capture something that looks promising in the green. Half a second. Well, thank goodness for the pause button on there, because the data that came up wasn't exactly what I was expecting, and I had to go look for the explanation on it. I was expecting all of my bits right in here, because this is the green byte. I was expecting all of those first 8 bits to be high. We can see that the first bit is high right in here. Okay, you can see the longer pulse right in there. And then I've got a whole bunch of zeros afterwards. And I'm like, well, if red was all red, why isn't green all green? Now, keep in mind that I wasn't individually controlling what was going on. I was using their definition of green. And if I go over to their library, so if you go to the FastLED website, where are we on here? Just Google FastLED, it'll get you to their website, and then it'll eventually take you to their wiki for this. Is right in here, they've got a list of all the different colors that the LEDs can display, and they're playing green. Here's that number. So there's your 0x, indicating this is a hexadecimal number. Red, sure enough, is 00, and we're seeing the 00s come through right there. But the next number in green isn't FF, it's 80, which is half of FF. Um, so that's why we're only seeing that first byte or that first bit turn on, is because their green isn't full intense green. It's kind of a slightly darker green coming out there. So it's actually green, but it's only green on for about 50% of the time. Now they've got a whole bunch of other colors in here, and you can see that there's a hexadecimal color code for each of the colors. And so what you're seeing is the hexadecimal byte data. Good thing we talked about hex recently, eh? So you can recognize DA as a number, D in the 16s column. So D is like 13 or something in decimal. So 13 times 16 plus A, which is 10. That would go into your red data right in there. And so some of them are pretty easy. Like if we look up red in here, they're all in here alphabetical, so you can type in the different colors. Um, Scroll down here to, uh, yes, I know, R comes before S. They've got so many colors. And there was our FF in our red column. That was why we saw all the bits on, was because it was 255 in there, or 1111111 8 times, whatever. So that's one way to control the colors, is by using all these words. I'm not a big fan of that. What I like to do is to come in here and I'll just edit this and I'll say LEDs 0, and then I'll enter the number code that I want myself using hexadecimal. That's one way to do it, okay? And that's 0x, okay? So if I want full green, FF 00, or sorry, FF is full red. This is going to be red, green, blue. So 00 FF 00. It comes out slightly different in the signals because the chips look for the numbers in a different sequence than the code looks for it. But right in here, now, instead of having 0080 00, I should have 00 FF fully on. And if I pump that up there, then I should see what I'm looking for on the green. And my green should get a little brighter right down here. I don't know if that really shows up on the camera. It was pretty bright to begin with. Let's take a look at what it looks like on the data. Okay, and there we go. That looks more like it. Long 1 bit, so 1, 2, 3, 4, 5, 6, 7, 8. So our green is high, all ones going along there. Our green is as bright as it can be, and the other two colors are off. Okay, so that's another way that you can adjust your color in there, is by manually entering it. There's in fact a number of different ways that you can set colors using the FastLED library. So you can come in here and you can say, use your array and pick the element that you want. And then you can use the hexadecimal like we did right there for red, green, and blue using your hexadecimal numbers. You can use the words like they did in their example, LEDs bracket 1 if you were referring to the next LED in line, and you could say equals CRGB. I think there's supposed to be 2 colons in there if I don't get me wrong, but if it doesn't compile, put a second colon in there. Or, and this is probably a nice way to do it, you can say LEDs bracket 2, okay, or 0 or 1, dot set RGB, and then you can use decimal numbers in here, and this will basically just take these decimal numbers and convert them back into hexadecimal numbers and pass that number into the element. And then keeping in mind, really, really important, okay, that you go fastled.show to send that data, because you build the array and then you send it down the line. Now, that's about it for using the FastLED library. You can do some really neat things with it. We'll take a look at a couple more examples. One thing to keep in mind as you start to develop plans for these brilliant LED displays, remember the power required to run large arrays is quite a bit of current. Okay, you need a really good power supply to do it. And your Arduino Uno has about 2,000 bytes of RAM. So you're limited to being able to control about 600 pixels from an Arduino Uno. All right. Let's take a look at a couple of the other examples on there. They've got a neat one in there called Cylon, and we'll take a look at how to modify that, talk about how it does, and then I'll let you try uploading some code and activating your NeoPixels. And now you'll know a lot more than just how to make it work. You'll have seen some of the magic going on behind the scenes. Okay, so in our examples here, there come some really neat examples with this. Let's take a look at the FastLED, and I'm just going to pull Cylon out of there. Now, not many of you are probably familiar with the original Battlestar Galactica, but when I was a young lad, there was a sci-fi show on TV. It was jealous of Star Wars, admitted it was trying to cash in on that whole thing, but it was about the only sci-fi show on TV at the time because Star Trek had been off the air for quite a while. And anyway, Battlestar Galactica, the bad guys were Cylons. Now, it's not the recent Amazon Prime or whatever remake where the Cylons were like kind of attractive looking people in rubber lizard masks or whatever the heck that was all about. The Cylons in here, they were stormtrooper knockoffs, but they had this one eyeball that just kept going back and forth across their face because they were robots. And so anyway, it was no wonder they could never hit the good guys because these guys only had one eye and it never stayed still. It kept moving back and forth across their face. So anytime you see reference to a Cylon program, it's referring back to a TV show that was on the air in the 80s. Anyway, and it's going to make the LED go back and forth across the display like like an blah, 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 like a Cylon's eyepiece. Anyway, first of all, we've opened up the Cylon code right in here. And like I say, anytime you're using the example code, there's a couple of things to modify. So you need to modify the number of LEDs. And you've got 8 LEDs in your strip. You need to modify the data pin. Which pin are you hooked up to? And you're hooked up to A0. Okay? Or whatever pin you're hooked up to. I'm hooked up to A0. If you're something different, that's perfectly fine. So this is, if you're going to write your own code, this is an important instruction right here. The serial begins, not all that important. This one right in here is important all the way along. And because that just sort of sets everything to some degree of brightness. And they've got a fade all instruction where when you see it call fade all in here, we've put our functions at the end. You can put them at the beginning if you want. And so if you see fade all, it's going to come in here and it's going to do a loop from 0 to the number of LEDs, and it's going to scale them down, scale their brightness down a little bit. Okay, so it says we can ignore some of the serial prints. It's going to say first slide it in one direction. Okay, and then it's going to come in here. It's going to show that, and then it's going to fade them, and then it's going to delay them, and then it's going to come down here, and then it's going the other direction. So we're going from number of LEDs to 0. Here we go from 0 to the number of LEDs, which means in one way it's going in one direction from 0, 1, 2, 3, 4, 5, 6, 7, and in the other way it goes 7, 6, 5, 4, 3, 2, 1, 0. Let's upload it and see what we get. Hope I didn't unplug anything there. Now, that's changing colors and bouncing around on there, but it's really not what I'm thinking of as a Cylon display. And I think it's trying to get too fancy in here. It's changing the hue and everything on here. And I'm just going to change this so that we can use one of our ways of controlling the LEDs. I'm going to use LEDs.setRGB. So I'm going to say right in here, LEDs I, okay, instead of equals, I'm going to go LEDs dot set RGB brackets. And what color should I make that? They were red in the original show, so let's go 255, 0, 0. And down here, instead of cycling through all the different hues like they're trying to do and be fancy, I'm just going to turn them off. LEDs I dot set RGB bracket 0, 0, 0. And now I'm going to hope that I typed that all in correctly. And it compiles and uploads. And now it's bouncing back and forth really, really quickly and distractingly on there. Okay, and that's because I've got this delay right in here set to 10. So let's set that to 100, this to 100, and slow things down a little bit. Now it's bouncing up and down, but that's still not quite the Cylon because it's not turning it off right away afterwards. Okay, so it's going up and down. It's kind of like a yo-yo, which is really good, but it's not the original Cylon. I want Cylon. Okay, so you can see that it's left in here a command, and they anticipated this. And what we're going to do is we're going to, after we turn the LED on and display it, we're just going to turn it off. So let's activate that. We'll let it use its black command to turn it off when we come down and when we go back up again. Okay, so now it's going to come in here. It's going to loop around and FastLED.show. It's going to turn that individual LED off before it turns the next one on. Oh, now we've got it going in one direction. So as you can see, you sometimes have to play around with these to get it going what you want. So we've got it working okay from the 0 to 1. It's working right coming up in this direction. Well, down here, we've got it turned off right here and turned off right here. Remember, we set that to color 0, 0. My mistake. I'm going to set it to a different color when it comes back down. We haven't seen a lot of the blue LED. Let's set it to 255 in here. Now you can blend colors in here. So if you want a little bit of red and blue in there, let's, I don't know, let's say 150 and I don't know, a little bit of blue. Let's try 120. See what we get when we put red and blue together. It might be pretty. Now, the cool thing about this, we're only using 8 LEDs, but if you had a whole bunch more LEDs, you could use more LEDs. And there we go. I kind of got purple coming back down. I'm not sure that's really, maybe if I, oh, doesn't work so well if I unplug it. I'll take that off the oscilloscope probe right there, plug it back in, and maybe if I just put a sheet of white paper over top of it, you can see that lovely purple coming down. Camera doesn't capture it quite so well. But there we go. We've got Cylon eyeballs bouncing back and forth across the display. If I turn out the light, maybe it shows up even brighter. And that's probably more than enough for today. You thought you were going to be talking just about the Neopixel strips, but in the process, we've covered everything from serial data communications, oscilloscopes, what's in the Neopixel and how the chip works, hexadecimal, what a compiler is and what a machine language and assembly language is, and I think your brain is probably full right now. I know I'm ready for, well, another sip of water. Have a good day, and we'll be back with another episode next week.